but today I'm going to be demonstrating pretty much using the ArcGIS Toolbox in ArcGIS Pro. So many of these functions can be done in QGIS, and you can also use ArcMap, but I'll just be focusing on the one platform today. So with that housekeeping taken care of, I'd like to jump in and get started on GIS applications for SAR data. We'll be focusing on flood mapping applications, but a lot of these tools can be used to detect any kind of change. To begin, I'd actually like to take a look at our new on-demand RTC Vertex products. So I'll open our ASF Data Search website. This is the default when you navigate to our search portal. You'll see the map and the geographic search type is selected. So in this platform, you can zoom into your area of interest, and you can just draw a square on the map, or as I mentioned earlier, you can also import an area of interest if you have a shapefile or a KML or a JSON. You select the data set that you're interested in. We'll be looking for Sentinel-1, but if you're looking for the PALSAR RTC, you can select that, or the Sentinel-1 InSAR beta products that I mentioned earlier, or UAV SAR. You can select whichever data set you're interested in for that particular search. The filters button opens additional parameters if you want to narrow your search even more than just the geographic location. I'm going to look specifically for data sets from the month of May. So I'll set those dates. You can also select additional filters, but I'm just going to start with that search there. Once that's complete, it shows all of the available data that touches essentially that area of interest. So if I see a footprint that covers the area that I'm particularly interested in well, I can just click on that to see more information about that specific granule. And one cool feature that I really appreciate is that if I want to see all of the acquisitions that are from that same path and frame, I can just click the More Like This button, and that will restrict the search even further to just that same path and frame. So now I've got a nice time series that are collected over the same patch of Earth. So we have acquisitions from the 3rd, the 15th, and the 27th of May. Now what I'm about to demonstrate is hot off the presses. It was just released on Tuesday, so you are some of the first people to hear about it in person. You can now submit a job to be processed for radiometric terrain correction directly from this interface. Once you've found a granule you're interested in, you simply use the Add to On-Demand Queue button to request processing for that granule. You can see that all of these granules have both single look complex and the ground bridge detected products available, and either of those products are suitable for generating an RTC product. The GRD is a slightly faster process, but you can choose either one if you prefer. I'm going to select the GRD and add it to my on-demand queue. And I'll do the same thing for the other 2 dates as well. Then I can open my on-demand queue. Oh, sorry. I can open my on-demand queue, and you can see that the 3 granules that I've added are listed. There's an option to enter a project name, and you can either type in something new, or if you've entered project names before, you can also choose from previous names. So I'm just going to add these to my Michigan Flood 2020 project queue or project name. And that allows for easy filtering of your products afterwards. The only processing type currently available is RTC using Gamma software, but there are additional processing options that you can choose. If you're not very familiar with these data sets, you can just leave these all as default. But if you have some familiarity and you have your own preferences, you can also change these options. You can choose between gamma naught and sigma naught radiometry. You can choose between power and amplitude scale, which I'll talk about more later. There's also an option to co-register the dataset to the digital elevation model. In some cases, this may give you a better RTC output, but we don't recommend it if you're planning to look at time series of datasets, because the digital elevation models that we use for RTC are global, publicly available products, and so the SRTM or the NED usually, and so they aren't always awesome for every area on Earth. And the geolocation of the Sentinel-1 granules is very good. And so it'll be in a better place on Earth if you just use the orbit files that come with the Sentinel-1 data. But if you really want to optimize your DEM and have it matched to the DEM, you can choose that option if you'd like. We don't recommend it, especially for time series. You can potentially get some jitter in your images, whereas if you just use the orbit files, the images tend to be nicely in line through time. You can choose to include a copy of the DEM that we use for RTC, and also the incidence angle map. If you're not interested in those products, you can leave that unchecked. It makes your download file smaller if you don't include them. But if you would find that useful, you can choose to add that to your package. And then you can also choose to apply a speckle filter to your product. This applies an enhanced Lee filter. SAR has speckle. That's one of the characteristics of SAR amplitude datasets. In some cases, it may not matter, but for some analyses, you may find that the speckle sort of throws off some of your calculations. Applying a speckle filter generally reduces the resolution of your data set, but it does smooth out the radiometric returns. So in this case, I'll choose to apply the speckle filter. At that point, I can submit my queue, and it will prompt you to view the on-demand products. You can either just click this button to take you to the on-demand results, or you can at any time go and see all of your on-demand products by just selecting on-demand products as your search type. So you can see that I have 3 jobs pending. These are the ones that I just queued up. Once they start actually processing, that status will change. And once they're complete, then they're just listed as having a zip file. If you want, you can restrict your results to just your particular project that you're interested in. So I'll just restrict to my Michigan flood products and click the search button. And now this just shows the products that I have that are affiliated with this particular project. If I scroll down to the bottom, you can see that I have some expired files. Once you request an RTC product, it is available for 14 days after it's been processed. After that, it is no longer accessible. It's deleted from our archive. But if you weren't able to download it or forgot about it, you can easily copy the scene name. So if you select one of your expired files, you can just copy the scene name and go to the list search, paste that scene name, and search for that particular granule, and then you can go ahead and resubmit it for analysis and generate a new RTC image. You can also choose to hide your expired files. So after you've been working in this platform for a while, you might get quite a backlog of expired files. And if you don't want to see them in your list, you can just choose to hide them. So once the product has been processed, it usually takes between 20 and 40 minutes, depending on the data set. Once it's complete, you can either select a product and just click on the download file button, and it will download that individual file. Or if you ordered a whole bunch of RTC products and you want to download them all at once, you can just add them to your download queue. And then when you're ready, when you've selected all of the products that you want to download, you can again just download them each individually, or you can choose a bulk data download option. If you download the Python script, this will download a script that includes all of the information needed to automatically download all of the files in that list. And you don't have to tend them at all. It will just do it automatically one by one. So if you have Python installed on your computer and in your path, all you have to do is double click that file. It will launch a Python shell and it will prompt you for your Earth data login credentials. And then once those are entered, it will just start downloading and keep downloading in the background until all of the files you've selected are downloaded. So that is how you can get RTC files on demand through the Vertex interface. The RTC products that we're generating use, as I mentioned, the Gamma software package, which is third-party software for processing SAR. And if you download the package, you'll see that there are a lot of files included. The ones we're particularly interested in are the actual RTC files, and those are GeoTIFFs, and they're annotated with the polarization of the data set. So in this case, I have vertical polarization as my primary polarization. So I have VV and VH data sets available. But there's a lot more stuff in that package. And if you're new to our products, I recommend that you take a look at the README file. You can either just open it as a text file and read that, but it is also in Markdown format. So if you have a Markdown editor or like to look at things in a Markdown environment, you can also open it with a Markdown editor. In addition, there is an XML file associated with every raster in the package, and this is accessible to ArcGIS. So if you are working with these data sets in an ArcGIS environment, you can either use the item description tab in ArcMap or the metadata tab in ArcGIS Pro and see all of the information included in that XML file. And as I said, there's one for every raster that's in the file package, and each XML is specific to the raster it's describing. And there's a lot of information about that particular layer and links to resources to learn more about it and various other hints and resources that are available. ASF has developed a custom toolbox for ArcGIS applications. It can be used in either ArcMap or ArcGIS Pro. And it was really designed specifically for use with products that are generated by Hype, which is what's working in the background when you order on-demand products from Vertex. So if you've ordered RTC products through Vertex, they behave fairly seamlessly in the toolbox. But you can also use other SAR data sets as long as they are appropriate for the specific tool that you're trying to use. To download the ArcGIS Toolbox, you can visit our GIS Tools website and just click on the button to download the zip file. You can extract that anywhere on your computer, and then you can just navigate to it within your ArcGIS catalog and use the tools as you would any other tool in ArcGIS. As I mentioned, I did give a webinar in July that goes through all of the tools except one. I'll be introducing one new tool that has been added to our official release since the webinar. Most of the tools are fairly straightforward. We just do the work in embedding the calculations that are required, but you can use the same workflow with tools that are natively available in both QGIS and ArcGIS environments. So that's outlined again in this presentation. I'm not going to dwell on those slides, but they're there for your reference. And you can also watch the webinar recording if you'd like. That uses ArcMap for the demonstration, and today I'll be using ArcGIS Pro. One thing to note is that most of the tools require the spatial analyst extension to accomplish the tasks. So if you don't have the spatial analyst extension for ArcGIS, you won't be able to run these tools. And if that's the case, QGIS is always a good option because that's a free and open source software. So we'll be taking a look at Midlands County, Michigan. There was intense rainfall this spring during May, and it resulted in flooding and also dam breaches. So we're going to be looking at some of these areas to map surface water and also look at detecting change. I'm going to open my ArcGIS Pro environment and just give you a little bit of an orientation to the region. So this is Midland County, Michigan. And let's just take a look at some Sentinel-2 optical data from before and after the flooding. So this is imagery from before the flood. I'm going to zoom into the Shiawassee National Wildlife Refuge, which had significant flooding. There are a lot of wetlands and low areas with lots of small streams running through them. And during the rainfall, many of those areas were inundated with standing water. If we look at the data that was collected on the 27th of May using Sentinel-2, you can see one of the problems with relying on optical data to analyze floods. In that right in the area that was most impacted by the flood, we have a really nice cloud bank that makes it very difficult to see what's going on the Earth's surface. So we're going to look at SAR data to map our water extent. I have extracted my ArcGIS Toolbox, and I'm going to expand the toolbox itself to see all of the tools that are included. The first tool we're going to use is the unzip files utility. This is just a simple tool to help you deal with the downloads from your Vertex custom products. So if you've downloaded a whole bunch of these zip archives and you want to extract them all to a project folder, this makes that really easy. I can just select the folder that contains my zipped archives and select the folder where I want them to be extracted to, and click OK, and click Run. Now this will look for every zip file that's in that source folder. So if you're just using your downloads folder as the source file or the source directory, it will extract every zip file that you have in there. So if you have a lot of unrelated zip files, you may want to move your RTC files somewhere else before extracting. So I'll run this process. And when that's complete, I can refresh my RTC folder and I can see that those products have been extracted. So I have data from the 15th of May and the 27th of May. I'm going to go ahead and add the VV layer from before the flood and the VV layer from after the flood. And you can see that there are significant differences in the backscatter from before and after. At this point, I'd like to talk briefly about some of the scales that are used in RTC datasets. I'll go back to my presentation just to help summarize. RTC products are often output in power scale, which is great for numeric analysis, but it often doesn't visualize very well. If you bring an RTC that's in power scale into your GIS environment, often you'll find that it's completely black. And this is because most power values are very, very close to zero. If, however, you have a couple bright scatterers in your image, that can really skew your dynamic range. So if you have a couple of pixels that have values of 7 or 8, or sometimes even 20 or 25, suddenly you're stretching your grayscale from very small to very large. And so even though almost all your pixels may be less than 0.5, your grayscale is still stretching to a much larger number. So everything appears very dark. And that's fine for, as I mentioned, for numeric analysis where you're not really concerned with looking at the image. But if you're going to be looking at a lot of the imagery, often the amplitude scale is a more pleasant scale to work with. This is simply the square root of the power values, and it tends to give fairly good visualization. The very small values, the very small decimals become greater, and the large numbers become smaller. So it kind of brings that dynamic range a little bit closer together. Another common scale is the dB scale, which is 10 times the log 10 of the power values. This is a good scale for differentiating among very dark pixels. And because most of the very dark pixels that you'll see in many cases, at least in North America, indicate the presence of water. So if you're trying to determine where water exists on the landscape, standing water exists on the landscape, using the dB to find a threshold to cut off often can be an easy way to identify water pixels. So we're going to go back to the ArcGIS interface and walk through how that process would work. Our first step is to convert our amplitude products to decibel. So I'll select my RTC products. Here's my amplitude VV. And because it's a HYPE product and it has a standardized naming scheme, the tool recognizes that the input is in an amplitude scale, but I still need to say that I would like it to be output as dB. By default, it will save the output to the same directory that contains your input file, but you can change that if you want. I'm going to save all of my products in a separate folder, so I'll save that to products. The default output name is the same as the input file name, but just tagged with a dB. So once I've entered all of that information, I click the Run button. And while that's thinking, I can start the same process for the other date. So again, I'll select my VV amplitude file and convert that to dB. Save it to my products folder. And click Run. Meanwhile, my original dB file has now been generated and added to my project. And you can see the difference already between the original amplitude data set from the 15th and the dB data set from the 15th. The water remains dark, but everything else really gets brightened up. And so there's a very strong delineation between the dark pixels that generally indicate the presence of water and all of the rest. So we're going to use this property of the dark surface water pixels to generate a water mask or identify where water occurs on the landscape. So the first step for doing this is simply to apply a symbology within ArcGIS. So we're not changing the data at this point, we're just viewing things and trying to figure out what's going on and what thresholds might work best for our particular application. So let's go ahead and start with the data set from post-flooding. And we'll change the symbology from stretch symbology to a classified symbology. I'm only going to have two classes. All I'm interested in is water versus not water. So I'll set the number of classes to 2. And I'll set everything that's not water to just be clear. So in order to determine the threshold, we can take a look at the histogram. And often in RTC datasets, you'll have this bimodal distribution of the pixel values. And this first peak that you see are those very dark values, which generally indicate water. And then all of the rest of the pixels are of higher intensity in terms of backscatter. So we can just interactively move this threshold. And what we're looking for generally, a good place to start when you're trying to delineate water is to find where the trough is between those two peaks. It can be sometimes hard to tell, but in this case, we can see that the very dark pixels from the 27th are fairly well delineated at this point. We might want to include a few more just to make sure we're not missing any major water. So we can see that that matches up pretty well with the very dark pixels. So you can either just select your threshold using this slider bar here, or you can also just enter a specific value in the upper value threshold. So I'll just enter that as -17. So all we've done here is change the symbology. If you were to bring this dB raster into any other project, it would still just be a grayscale stretch. We've just changed how it looks in our particular project. Let's go ahead and do the same thing with the dB file from the 15th. So we'll look at the symbology and set it to classified with 2 classes. Again, we'll set non-water to be clear, and we'll give a different color for the water. If we look at the histogram, you can see that the peaks are not nearly as clear as in the original image. So we'll have to be a little bit more creative in guessing where the trough is between those two values. So we can compare it to the original amplitude data set. And that looks pretty good. For simplicity, we can just set it to be exactly the same as our other water masks. So we'll just enter -17. All right, so we have our two masks. If we look at them both together, you can see that we mapped a lot more surface water post-flood than we did during the flood or before the flood. So as I mentioned, we've just changed the symbology. This is nothing permanent. You could either, you could just save this as a layer, a raster layer to preserve that symbology. But in some cases, you may want to actually do analysis using a water mask. And so you can actually generate an entirely new raster that only shows the water pixels. So you can use the Classify RTC tool to do that. And you just select your DB file. So we'll create one for the post-flooding imagery. We'll save it to our products, and then we can enter the threshold. So we chose -17. I often like to change my output file name so that it indicates what that threshold was. Sometimes it's nice to generate a few different ones and use them in an actual application just to see which one actually aligns best with your particular use case. So we'll generate that RTC mask. And if we compare, you can see that that's an exact match to the way that we classified the image. But the difference is that if I click on one of these pixels outside of the water mask, it will be no data, whereas everything within the water mask will have a value of 1. So then you can use that for analysis if you want to do any calculations with using other layers for presence, absence of water. At this point, I'd like to zoom to a different area. We're going to focus in on Edenville, where there was a dam breach caused by the flooding. So in our amplitude data from before the flooding, you can see that there was a fairly large reservoir. So a lot of surface water is indicated in this region, whereas our water mask from after the flooding shows that there's hardly any water left. So another way to take a look at significant changes on the landscape to help you identify and locate places where things have changed in terms of backscatter is to calculate the log difference between two images. So basically, you're just taking the log of a ratio of a newer image against an older image. So we'll select our input raster with from our newer acquisition. And this tool works best with amplitude data, although it also is fine with power. If you tend to use one or the other, you'll find the values are a little bit different than you might expect, but either one of those works fine. I don't recommend using DB inputs with this tool because DB products are already in a log scale, so you're applying a log to a log. But you can use either amplitude or power. So I'll select the VV amplitude from the newer acquisition on the 27th, and then select the amplitude from the 15th, also in VV polarization, and I'll save that to my products folder. And the default name is very long, and are welcome to change that. It just takes the names of the two input files and then tags it with a log difference. So I'll go ahead and run that calculation. And you can see it is, by default, it symbolizes in a simple grayscale. In this case, even in a grayscale, you can see that something clearly happened here and something clearly happened here. Changes are not always quite as distinctive, so it may be useful to change the symbology of this raster to kind of help you identify the areas where change is most prevalent. So we'll open the symbology and again, change the classified symbology. I'll leave it at 5 classes. And if you click on the More button, you can show statistics, which will tell you the standard deviation and mean of your values. So if there's no change, we would expect values to be very close to 0, plus or minus a little bit. I often use the standard deviation to set my thresholds for the different classes. So we'll go ahead and use approximately 2 standard deviations. So we'll set this one to minus 0.3 and minus 0.15. Then positive 0.15 and positive 0.3. And I'm going to choose a different color scheme that has different colors for positive and negative. Oops. So once you've set this color, all of the data that's shown in yellow, there's not a lot of change. So it's probably not significant. But once you're getting above that plus or minus 0.15 mark, that may be significant. And then above the 0.3, we expect that that's a pretty significant change in backscatter. Positive values indicate that the backscatter from your second acquisition is brighter, or there's a higher backscatter than there was in the original image. Negative values indicate that the backscatter has decreased. So if we look at this reservoir area, it's very clear that there was a significant increase in backscatter. Now this makes sense if we think about the image. When there was a reservoir, there was that nice smooth water surface. Water's got high dielectric properties, so all of the signal pretty much just bounces off unless it's a super windy day. But in our case, it was very dark. When that dam breached and that reservoir was drained, what you have left behind is this saturated soil that was underneath that water reservoir. Saturated soil tends to have very high backscatter, much higher than a dry soil, for example. So you've gone kind of from one extreme to the other, where you had extremely low backscatter from the surface water, and then suddenly you have very high backscatter from moist sediments that were underneath that reservoir. If we look at the negative values, that's a kind of a more interesting story in some ways. So clearly things changed here, but it's not clear what would drive that particular change. These negative values indicate that the backscatter is lower in the more recent acquisition than it was prior to the flood. And some of the drivers for a lower backscatter return would be that the surface has gone from rough to smooth. It's been smoothed out in some way, or it has gotten drier. So if you had fairly saturated soils and you had a drying trend, you would see a lower backscatter in the drier soil than there was in the wet soil. That seems a little counterintuitive after a flood, but I'll dive in a little bit deeper in a moment. But the other potential driver for a decrease in backscatter could also be inundation. So if you have soils that are getting more and more saturated, the returns are getting brighter and brighter, and then suddenly you have surface water. So it's gone from soil saturation until it can't hold anymore and you get actual inundation and water pooling on the surface. You'll have a very distinct change from brighter backscatter to suddenly very dark backscatter. Now, that doesn't seem to be what's happening here. And what may be at play is that the images that we used were collected by Sentinel-1 about a week before and about a week after the peak flooding. So what may have happened is that that flood water has already receded, and often agricultural lands especially, or kind of more barren lands that have been flooded or inundated or extremely saturated by water, dry out in a way that leaves them kind of cracked and brittle. And so what we may be seeing, and if we zoom to the entire granule, you can see that this is a really prevalent trend across that region, is this lowering of backscatter. So what might be happening is that you have left behind these sediments that are fairly desiccated and possibly smoothed out. Especially, it was fairly early in the agricultural season for many crops, and so it's possible that crops that were plowed or turned may have gotten evened out actually by all the flooding. So it's a fascinating trend, and it really illustrates that when interpreting SAR data, there are not always clear answers that you can globally apply. You need to consider the actual situation where the data was collected and be aware of the factors that might be driving these changes. It's a great tool for identifying change, but often you'll have to kind of pull in other data sets to really understand what's going on. To that end, let's go back to our Shiawassee flood region. We can see that some of these dark areas match up very well with the flood map that we delineated. So many of the dark areas show up in our flood mask, but there are these other dark areas that do not. And if we look at other imagery, it's clear that these are probably not inundated. So they fit more the pattern of the other regions where you're getting a decrease in backscatter, but it's not driven by flooding. So with that, I'd like to take a look at one of our newest tools, which is the RGB Decomposition tool. If you download our data sets from Vertex, our RTC products, it includes an RGB decomposition browse image that is a false color red, green, and blue. However, that's just a browse image. It's resampled, and so the resolution is not very high. It may give you what you need, but if you want a full resolution version of that, you can actually process that directly from the VV and VH or HH and HV RTC products. It does need to be dual pole, however. It uses both the copole and the cross pole data sets to generate the RGB. So I'll select one of my RTC products, and it recognizes again that it's amplitude and that the primary polarization is vertical. If you're not using a HYPE Sentinel-1 data set, then you would need to set these automatically. I'll set the output again to be my products folder. And then I would click run. This actually is a fairly complicated process. And so this is one that if you look at the slide deck, I don't break down how what all calculations are involved. It's quite a series of calculations and it takes a while. So it won't probably finish before the end of this session. So I'm just not going to kick that off at this point, but you would if you wanted to actually run these. I'll use a pre-processed version. So we can take a look at this RGB file. And on the website for the course, there is also a link to the documentation for the RGB decomposition that we use with the Sentinel-1 datasets. And if you are interested in working through those steps in QGIS or in a Python programming environment, it does walk you through all of the steps that are required, and you can follow along with that. It's just not quite as point and click as if you use the toolbox. So I'm going to zoom to this layer, and this is the image from after the flood. I'll also add the image from before the flood, and we'll talk a little bit about the symbology. So basically, our RGB decomposition makes use of the VH, so the cross-polarized returns, or the HV, to generate the green areas. So those indicate, if there are high VH returns, that usually indicates the presence of vegetation. So that's assigned to the green channel. The blue channel is applied when there are very low returns in both the VV and the VH. Red is used when there are fairly low, when there's some volume scattering, but it's higher surface scattering as well. So you have higher values than the blue in both the VV and the VH, but the VH isn't as high as for the green areas. So in general, the green areas will indicate vegetation, the blue areas indicate water, and the red areas indicate something else. So often urban areas will appear more red, or agricultural fields that don't yet have a lot of vegetation may be more red. But in some cases, you get things that are maybe unexpected. So all of this blue, if you were to just look at that and say, oh, well, blue is water, it would be misleading. There are other conditions that also result in those blue colors. And if you were to look at an RTC, an RGB decomposition from Cairo, you would have a very hard time telling the difference between what is water and what is desert, because amplitude data gives very similar returns for surface water as for very dry desert sand, for completely opposite reasons. So the water has high dielectric properties, and so it's just sending everything off. All the signal is being reflected off into the distance. Whereas sand actually absorbs that signal, and it absorbs it so well, especially if the sand is dry, that signal can penetrate so far that by the time it gets scattered back, it doesn't have enough energy to make it out, so that it can't be returned to the sensor. So basically that signal is extincted. So in both cases, you have extremely low backscatter, but it's for completely opposite reasons. If we zoom into our RGB, we can see that there are differentiation between the different types of blue. So we have some areas which line up with our flood map very well. And those are those dark blue areas. Whereas the others, their radiometric returns make it so that they fall into that blue area, but it's not the same blue that indicates water. So when you're looking at RGB decomposition images, they can be very helpful just for understanding what you're seeing, but it's very important to keep in mind that this is a false color image. This is not surface reflectance. It's not a replacement for optical imagery. Another area where you can be led astray is frozen ground. So if you're looking at Arctic tundra, it may, in some cases, also look very blue, which does not indicate the presence of surface water. So with that, I'll just mention briefly that we have a new tool that we're developing, which is the ability to create a water mask from an RGB image. So rather than just using a single pool data set to generate your water mask, you could actually use the RGB, which integrates both VV and VH signals. So there is, in some cases, more robustness to that, especially if there are windy conditions. You may find that you can still get a pretty good water mask even in windy environments, whereas if you were just using the VV, you might not be able to recognize the water. So this is under development, and I've included the link to our RGB water masking development version of the toolbox. And if you're interested in kind of playing around with that tool, and especially if you give us feedback, we're trying to dial in what what are good default thresholds to use for that? And so any feedback would certainly be welcome. We're getting down to the end. I'll ask if there are any questions, and if not, then I'll do a very quick demo of how the RGB water masking works. But any questions in the chat so far? I'm not seeing any, so I'll go ahead and just do a very quick introduction to the water masking. So this water mask just takes an RGB decomposition image as an input. So I'll select one of my pre-processed RGB. And then these are our current default thresholds. And you can set it to, again, output to wherever you would like it to be. And it's tagged with a water mask. I'm not going to run that because, again, it takes a little while, but we'll take a look at a couple of the options. So I've run a mask just using the default settings. So you can see this mask was generated for the pre-flood using the default values. So if I zoom out, you can see that it masks the lake really well, which is a little bit surprising because there was a lot of wind that day. And so if we had done the same thing, if we look at our water mask that we generated just with the VV, you can see that there was a large chunk of that lake that wasn't considered water. So this was a much more viable tool for identifying the water in that large lake, but it went a little overboard and probably misidentified some of the terrestrial areas. So I adjusted some of the thresholds and came up with a green value of 50, a red value of 0, and a blue value of 10 in the threshold selection parameters. And when I run that, if we zoom out, we'll see that again, that was more in line with the VV. So it didn't do as great a job masking the large water body, but it did a much better job of identifying what's probably actually water on the terrestrial landscape. So the purple area, those were the ones that are probably false in the original water mask, and the pink ones show what is likely to be actually water in the image. So anyway, that's another approach to looking at water.